We already did now this part. We showed if you know the potential at every point in space, how can you get the electric field? And we started actually, it's a definition. We defined the electric field to be obtained from the potential this way. So this is something we did in detail, and you should have solved many examples and problems related to this before you continue. So now that we know this, how can we address the other question that we need to know in order to complete the whole picture? Remember, the whole picture, we need to start with a charge distribution and get the electric field. The first step is to get the potential itself. We didn't do that yet. We don't know how to get the potential itself from the charge distribution. All what we did was we got the electric field from the potential. So now we want to attack this point and try to see how can we get the potential when you know the charge distribution. And it's going to take a bit of time, a while for us to do this completely, so it'll take a few steps. To start, the first step we're going to do is we're going to say, okay, here there's a charge distribution in space, and there are two very, very close points right next to each other, separated by a differential vector dr. How do we get the difference in potential between these 2 points that are very, very close? This is going to be our first subject. And then we're going to say, okay, what about how to get the difference in potential between 2 points that are very far? Any arbitrary 2 points. This is going to be the second thing we're going to do. And then based on that, we're going to learn how to get the potential field from the given charge distribution. So this is the sequence of steps. This is the fundamental starting point we're going to begin with. We're going to start in these slides by seeing how can you get the difference in potential between 2 points that are very, very close. So let's review the concept of the differential for a function of one variable. If you have the potential at x and the potential at x plus dx, what's the difference in potential between those 2 points? The difference in potential is the derivative of the potential with respect to x times dx. This is something that we know from math, and we've used this concept several times when we found the area between two circles of very close radii. The difference in value of a function at a point and a nearby point, you get it by differentiating the function and then multiplying by the difference in distance. So this is for a function of one variable. It's pretty easy. About if you have 2 points in space that are in 3 dimensions, so point A has coordinates x, y, and z, and point B has coordinates x plus dx, y plus dy, and z plus dz. So you move from one point in space to another point in space in 3 dimensions. How would you get the difference in the value of a function, in this case the potential, at point B and at point A? What would dV be? dV is the potential at point B minus the potential at point A. What would that equal to? We're going to give the details in the next video for people who want to know the details, the mathematical details, but I'm giving you here the final result. The final result says that the difference in potential for those very 2 nearby points in the limit when dx, dy, and dz are very, very small differential elements of length, the difference in potential is the derivative of potential with respect to x, partial derivative, times dx, plus partial derivative of potential with respect to y dy, plus partial derivative of v with respect to z dz. So you can see, compared to the one-dimensional case, you have to take into the consideration that the potential changes with x, but it also changes with y, and it also changes with z. So that's the added complication that you have in 3 dimensions that you don't have in 1 dimension. So this is the summary of what we just said, that the difference in potential between 2 nearby points, it's given by this. Okay, can we get this in a different way? Let's see. So let's take 2 nearby points, those 2 nearby points. Let's make a vector dr that points from A to B. So the vector dr has dx in the I direction, dy in the j direction, and dz in the k direction. The electric field at A is given by this vector EA. So this is the electric field at point A. If you take the dot product and multiply by -1 of E dot dr, and you multiply by -1, let's see what this gives you. It'll be clear why we're doing this in a minute. So there's the negative sign, and the electric field is this. This was the fundamental definition of the electric field in terms of potential. And then there's the dot product, and then there's the dr vector. So when you take the dot product of these two brackets, the I gets dotted into the I gets dotted into the J and the K, but I dot J and I dot K is 0. So the only terms that survive are the first term with the first term, the second term with the second term, and the third term with the third term. So when you multiply out and the minus signs will cancel with the minus sign here, this result. But do you remember what this was? We just showed what this was a while ago. Mathematically, what is this? It's just the difference in potential between two nearby points. So we've arrived at a result that the difference in potential between 2 points that are very close is just the negative of the electric field dotted into the displacement vector from one point to the other. If you want to write it a bit more detailed, so I write it as dV B minus A because I'm getting the potential at B minus the potential at A. It's equal to minus the electric field at A dotted into the vector, the displacement vector from A to B. And so this is a fundamental result that in itself is a very important result, and we're going to be using this result a lot in the lab when you're going to be mapping electric fields in the experiments in the lab. So this equation is already important in its own right, and remember it's coming from this fundamental definition that we gave for the electric field and potential.